Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thesis research. Today I'm going to be talking about some joint work with Federico, who I guess is still asleep or something like that. But anyway, so if you're interested in seeing the other talk, then I assume it's videotaped somewhere. So let me start by giving the program of my talk. So to start off with, I'll give an intro to what's known as the Bergman complex of a matroid. And for motivation, I'll explain some connections to tropical geometry. And
Lottie just said it sounds good, yeah. Especially in this weather, it sounds fantastic.
yeah, I can say more about tropical geometry if I haven't satisfied your interest with my bit of motivation. And then there will be a brief intermission where I review some facts about matroids and, well, definitions, matroids and oriented matroids. So then I'll introduce the main character, which is the Bergman complex of a matroid. I'll then, whoops. Sorry, I'm a mathematician and a combinatorialist, but so then I'll talk about the positive Bergman complex of an oriented matroid, and this is joint work with Federico and also with Klivans. And then finally I'll talk about the positive Bergman complex of a Coxeter arrangement. And there are connections here to what are known as graph associahedra. And this is joint work with, again, Federico and also with Victor Reiner. Okay, so stop me if my writing becomes too illegible or I start speaking too quickly. Okay, so first of all, as some kind of generic motivation, one point I'd like to make is that Bergman complexes of matroids are just, and here I'll denote this by script B of M, these are matroidal analogues of tropical varieties. Who here has heard anything about tropical geometry? It's kind of a, okay. Just as a few words about tropical geometry. Tropical geometry is what happens when you try to do geometry over the semi-ring of real numbers together with addition and the minimum operation.
Why is it called?
It's called...
Oh, because of the meridian?
Oh, I didn't think of that. The story I had heard is that it was invented by a Brazilian mathematician, and then some French scientists saw this work and did some more work and decided Brazil was in the tropics and called it tropical geometry.
That's a good explanation.
What did you say?
Even worse than the Chinese postman, because then at least they identify the country with the
Yeah. Yeah. I can say some more about tropical varieties, like definitions and stuff later. But you can ask me in the question sections if we have extra time. But let me just give you a vague overview of Bergman complexes. So first of all, an ideal I generated by linear forms has the structure of a matroid, M sub I. If you don't know what a matroid is, oh hey, I'll explain in a few minutes, so you can just.
We're trying to call you.
So for the purpose of the next couple minutes, you can just treat a matroid as some structure that I'll explain soon. So now the observation of Sternfels is that the tropical variety associated to such an ideal I depends only on the matroid structure. So if you have this kind of ideal, its tropical variety depends only on the matroid associated to that ideal. And so this allows you to, more generally, define the tropical variety of any matroid. And Sternfels called this the Bergman complex of that matroid.
Can you give us an example of this so that, to me, it's helpful?
An example of a matroid or a Bergman complex, or
A Bergman complex.
yeah, I'll give that in a few more minutes.
Okay.
Yeah, I'm going to define everything from scratch. Bergman.
Pretty arrogant if he named it after himself.
Yeah. Bergman did some. I guess Bergman didn't call. Bergman studied what essentially is the tropical variety of an ideal. He didn't call it such, but he defined essentially the Bergman complex of an ideal. But I mean, Sternfels came along and generalized it to matroids and then called it the Bergman complex in honor of Bergman. So, and then, well, I guess, should I use this board too, or is that?
I think
that,
it's,
okay.
well, we would get more
We can move.
exercise that way.
I want to write one more bullet point, but I don't know if you'll see it if I write it on this last line, so maybe I should just write it somewhere else.
Actually, when Federico gave his talk about matrix, he used this corner there a lot too.
Okay. So just kind of the overall picture that you should have is that Bergman complexes of matroids kind of correspond to tropical varieties, and then now I'll say a few words about an oriented matroid analog of this, and I'll define matroids and Bergman complexes after just setting up this overall picture. So the analogous thing for oriented matroids is that positive Bergman complexes, B plus of M of oriented matroids are oriented matroid analogues of what are known as positive tropical varieties. So just to kind of say where this comes from, one can define the positive part of any tropical variety, and then again, when the ideal is linear, it depends only on the oriented matroid structure of that variety. So when the ideal I is linear, this depends only on the oriented matroid structure of the ideal. And so then this implies that, well, this leads to a definition of basically the positive tropical variety associated to any oriented matroid. Okay, so Bergman complexes of matroids correspond to tropical varieties, and positive Bergman complexes correspond to positive tropical varieties. So I just brought this up because the tropical geometry is one of the main motivations for introducing these Bergman complexes of matroids. But if that's not good motivation for you, then, well, two things. I can explain something about tropical geometry at the end, and the other thing is perhaps the results will convince you that these are interesting things to study. Okay, so now let me review something about matroids. So how many people know what a matroid is? Okay, should I give some examples, maybe give the definition, just to review things?
Sure.
Okay. Okay, so so roughly speaking, a matroid is just a combinatorial abstraction of the notion of a set of vectors together with their relations of dependence, of the notion of a set of vectors together with the relations of, say, linear dependence. So objects that have the structure of a matroid include, well, as I said, a set of vectors in a vector space. There's also, you can think of it as a set of points in affine space. Another example is a graph, and here cycles will be your analogues of dependence. There's also an ideal generated by linear forms, and also hyperplane arrangements have the structure of a matroid. Okay. And oriented matroids are analogues of matroids, except that they also take into account data of orientations. So
what's the dependency in the case of the ideal?
it's relations in the ideal. Okay, so let me give you the rigorous definition of, say, an oriented matroid, since that encapsulates the definition of a matroid as well. And as I give this definition of oriented matroid, you should think about a directed graph together with its minimal cycles. Okay, so here's the definition. An oriented matroid M on a finite ground set capital E, and usually for me this will be, say, the set of points 1 through n, is, first of all, a non-empty collection C of what we call signed circuits. And these circuits are going to be signed subsets of E such that the following axioms hold. So the first axiom is that the empty set is not a signed circuit. So let me draw a picture of a graph to go along with this definition. So we want this to be a directed graph, and I'll label the edges. So in this example, the ground set is just the set 1 through 6, and the circuits are going to be directed cycles in this graph, minimal directed cycles. So we don't want the empty set to be one of these circuits. Sorry?
Find a directed cycle here.
So 1, 3 bar, 2.
Oh, 3 bars. So,
Yeah.
So you
Yeah,
allow
so
the bar.
That's right. That's right.
Otherwise, I was having some.
Yeah. Yeah, I should have said signed cycles.
Okay.
If capital X,
Yeah, well, I guess you did say mine.
so if capital X is a signed circuit, then so is minus X. So of course, 1 bar, 3, 2 bar is also a circuit. And no signed circuit properly contains another. So we just want our circuits to be the minimal cycles. And then finally, and this is the more complicated one, if x0 and x1 are signed circuits with x1 not equal to the negative of x0, and we take an element which is in the intersection of the positive part of this circuit and the negative part of this other circuit, then
So what are the positive and negative parts of the circuit? Or are they just the things that are in the
so here, yeah, the positive part here is 1 and 2. Yeah, that's right. And the negative part is 3. So then there is a third circuit, X in C, such that the positive part of this third circuit is contained in the union of the positive part of the original 2 circuits minus this element E, and an analogous statement for the negative part. X minus is contained in X0 minus union X1 minus, take away E. So this is saying that if you have 2 signed circuits that have some point of intersection, you can build a third one out of the 2 that avoids the middle element. So, if we were looking at this circuit 1, 3 bar 2, and 4, 5 bar, 6 bar 3, then we can build this third circuit, that traverses the 2 of them but skips the intersection.
I have a question. So your circuits are signed, you say signed subsets. Are they not more like signed sequences because the order matters, right?
Oh, they are sequences, but the order doesn't actually matter. I mean, in a graph they are sequences, but the order doesn't actually matter.
It does, right? Because if I interchange sort of 4 and 3, I mean, I can't say that 3, 5,
These are
4,
edges,
6.
not vertices.
No, but I can't say that 3, 5, 4, 6 in your example is a circuit.
Well, so I should have written this circuit C as 1, 2, 3 bar. I mean, I'm not actually thinking about it as a sequence of edges that I'm traversing. I'm just thinking about it as a subset.
As the edges in a circuit.
That's right. Yeah. Okay, so this is the definition of an oriented matroid. And if you just forget about the signs, then what you have is the definition of a matroid. So, okay, so let me give an example, which is an example I'll come back to repeatedly.
What do you mean? Sorry, it's just saying you have 2 intersections. Oh, that.
Okay, so this is going to be an example of an oriented matroid coming from a set of points in affine space. So let's let capital E be a set of points in Rn, and here our circuits will be minimal affine dependencies in Rn, which are contained in E. So here's a concrete example. So what I'm drawing, you should think of as the matroid of the points 1, 2, 3, 4, 5, 6. So the only reason I put the lines here is to show you where the dependencies are. So here, our ground set is a set of points, and circuits are just minimal dependencies. So for example, there's a dependency between 2, 6, and 3, which we would write as 2, 3, 6 bar, because 6 is in the convex hull of 2 and 3. There's also the dependency 1, 2, 3. Well, actually, maybe this is a better one. 1, 3, 5.
So I couldn't do this on the torus, for example, because then I wouldn't know what was in the convex hull of what. I mean, if I had a circuit that went around the torus, right, if I were trying to do it in the torus instead of an Rn.
How do you
Then I
define an
wouldn't-
affine dependence?
What?
I mean,
Define an affine dependence.
Yeah, I mean, you would only be caring about the affine
In a
dependencies.
linear space, in an affine space.
But you can get oriented matroids from pseudo-line arrangements. So there are things more general than this example here.
How did you get 1, 3, 5, 6?
This is because the span of 1 and 3 intersects the span of 5 and 6.
So you write down a dependence and you look at which things are positive and which are negative.
That's right.
And
Yeah.
what does the dependence mean? The dependence are your circuits.
Yeah, the dependencies are the circuits. Well, the circuits are the minimal dependencies. Yeah.
Why was it 5 bar 6 bar and not 5 6?
This is, well, I mean, if we were just talking about an ordinary matroid, then I wouldn't have put in the bars. But since I'm talking about an oriented matroid, well,
How do you know which is in the convex hull of which, I think is the question. How do you know?
Imagine writing
Oh.
dependency down with
Yeah.
coefficients. You look at which coefficients are positive and which are negative.
yeah, that's exactly right. Yeah, if you were to write down the equation, you would want to manipulate things so that you have positive signs, and then you'd look at what's on what side of the equation. Okay, so there's a bunch of other circuits, but I won't write them all down. And now let me just give one more matroidal definition, and then I'll introduce the main character of this talk. So this is going to be definitions of rank and flat of a matroid. Rank will be quite intuitive, I think. So let's let capital M be an oriented matroid. And now an independent set of M is just, well, you can almost guess it. It's just going to be a subset of E which contains no circuit. A subset of E which contains no circuit. And the rank of a set A contained in E is just the size of the largest independent set it contains. So, yeah, no surprises here. And then we say that a set A contained in the ground set is a flat if the rank of that set union an element is equal to the rank of A plus 1 for all x not in A. So this is just saying that a flat is a subset of the ground set that's kind of maximal with respect to rank. So for example, if you have the matroid of a set of points in Rn, flats are just going to be intersections of the points with an affine subspace. So 2, 6, and 3, these are the points that are the intersection of this set of points with this affine subspace right here.
So if I have an oriented graph, then an independent set of vertices has nothing to do with your independent set.
No.
That's right. Yeah. Yeah. Okay, so now let me finally get to the Bergman complex of a matroid.
So why do people not call it a tree?
I mean, I don't know who first came up with the definition of a matroid, but one thing is that matroids coming from sets of points are more general than those coming from graphs. So borrowing terminology from trees is maybe not the most general thing that you could do.
Linear independence predates independence in graphs, I think. Right? Yeah.
Okay, so now we get to the Bergman complex of a matroid. Okay, so let's let capital M be a matroid on the ground set, say, a set of points 1 through n with circuits C. And now, for an element omega, this is going to be an n-tuple of real numbers, and we're going to call this a weight vector. Well, we say that the omega weight of I in n is omega sub I. So this weight vector is just an n-tuple of real numbers that assigns weights to every element of the ground set. And now here's the definition of the Bergman complex. So the Bergman complex B of M of the matroid M is the set of weight vectors. A priori, these are just n-tuples of real numbers, but actually we're going to be viewing them on a lower dimensional sphere. So it's the collection of weight vectors such that every circuit achieves its maximum weight at least twice. So this looks like a very weird definition. I know. But it's an analogy with the definition of a tropical variety. I mean, at this point I could define a tropical variety if you want that for motivation, or else we could just kind of work with this definition for the moment. I should close this.
Is there a quick explanation of what the analogy is? Because I know what a tropical variety is, but this doesn't look like that to me.
So
I'm missing something obvious.
So there's one definition of a tropical variety associated to an ideal, which is as follows. It's a set of, it's the set of, well, you also have weight vectors here. It's a set of weight vectors, W and Rn, if your ideal is an ideal in n variables, such that the initial ideal with respect to that weight vector contains no monomial. That's one definition. And if it contains no monomial, in particular, every element in sub W of I is at least a binomial. In particular, every element of the ideal has two terms achieving the minimum weight or maximum weight. I can
I don't, for me, since I don't know what a tropical variety is, having this be an analogy, that maybe I'll understand tropical varieties on the basis of Bergman complexes later on. But
I mean, I can explain tropical varieties in 5 minutes. It's just a matter of whether.
So why
yeah,
is
an hour.
I'm
Why
okay
is it
just
Sn
going on with
minus
this.
2? I don't understand.
So this is the following sphere. Here, S of n minus 2 is the set of these n tuples such that their sum is 0 and the sum of the squares is 1. So it's a lower dimensional sphere, and it makes these things easier to visualize. Okay, so
Is this relevant for the definition? I mean, you could shift the vector up you can scale it, and that wouldn't change the definition.
Yeah, I mean, it doesn't really change the object that you're looking at in any important way. It just makes pictures easier. So at this point, let me do an example. Okay, so this is going to be an example of another point configuration, but this time very simple. It's just the oriented matroid of the following 3 points. So who can tell me what the circuits are? That's right. Sorry. If you notice, for the purpose of this definition, we can look at a matroid or an oriented matroid. So, I mean, it's fine to write down the signed circuits, but we could just think about them as subsets. All right. So let me just write this down as well. We also have 1 bar 3 2. Okay. So B of M is the set of three tuples in this lower dimensional sphere, such that, now if we look at this definition, we want every circuit to achieve its maximum weight at least twice. And here the circuits contain all 3 elements. So we want, this will be the set of 3 tuples such that, say, omega 1 is equal to omega 2 is greater than or equal to omega 3, or omega 1 is equal to omega 3 is greater than or equal to omega 2, or omega 2 is omega 3 greater than or equal to omega 1. Because these, I mean, the circuits here are just, the circuit is just the 3 tuple of numbers. It's just the collection of numbers 1, 2, and 3. And we want the corresponding weights on these 3 numbers. We want the maximum to be achieved at least twice. So these are the possibilities. Okay, so a priori, each of these sets is 2-dimensional. But if we were to view it in this sphere, scaling such that the 3 tuple of numbers sums to 0, we would get 3 rays like this, where the middle point is 0, 0, 0. And then if we further intersect with the sphere that requires the sum of the squares to be 1, we just get 3 points.
You call it a complex. And sort of, so usually, I mean, when I have complexes in geometry or algebraic geometry or so, you have boundary operators and stuff like that.
Oh, it's not that kind of complex. It's a polyhedral complex.
Is this the generalization of Gale diagram?
I'm not aware of such a connection, but
But a polyhedral complex has something like that. It has edges and facets.
So right. So in general, there are edges and facets. In this case, it's very simple.
These are edges and facets. I mean, how does it follow from the definition? How would you define edges and facets?
I mean, I think maybe it takes a little bit of work to see that it's a polyhedral complex. But I mean, in this example, it's just 3 points, and so 3 points are trivially a polyhedral complex.
One of the things that Bergman proved is that this object is basically a bunch of polyhedra glued together, and that's why it's called a polyhedral complex. But it's not trivial that this is true. It's a theorem of Bergman that it is.
Right, and in the case of, well, maybe I'll give a, maybe I'll stop to give a small result about the Bergman complex so that you can see how nice it is.
So do you have sort of in general, so it's a polyhedral complex in higher dimensions, right?
What do you mean in higher dimensions? Oh, I mean, yeah, it is. I mean, even when we're not looking at such a silly example, it is a polyhedral complex.
Right. So
You
it's
mean higher?
so it's a polyhedral complex in n dimensions.
I mean, if you specify what are the two elements in each cycle which maximize it, then there is a finite number of linear inequalities and there's a finite number of ways to specify.
Yeah, that's right. That's right.
So I can think of it actually as a polyhedral complex in Rn or not?
Yeah, I mean, it'll be a fan. It'll be a polyhedral fan in Rn.
So then I have the whole thing. I mean, I have the whole complex structure that I have sort of points, edges, plaquettes, and so on. So I have the d-dimensional, the k-dimensional cells. Just if I view it as a cell complex, then I can look at sort of the lower dimensional.
What's a plaquette? Or?
Plaquette is it's a physics. It's a fundamental face.
Oh, okay.
Okay, going up
So-
from edges
Oh,
to
okay.
fundamental.
So you
That's
have
a-
one-dimensional
Comes from
hypercube, two-dimensional
mathematical
hypercube,
physics.
Okay.
three-dimensional. So you have all these, I mean, not necessarily cubes, but you have one-dimensional cells, you have two-dimensional cells, up to n-dimensional cells.
Okay.
Right, so it's a two-dimensional cell as well.
So do you have the whole? So do you have boundary operators? Can we talk about the geometry, whether it's sort of this
Saying in
trivial?
the trivial way, in the way that you talk about it for polygons.
I mean, it's
I don't know, but
so.
it may not have DD. I mean, not every closed object
So-
may be a boundary and stuff like that. So can we do all this geometry on it?
What?
The polyhedral complex. So you have everything, yeah. It's not necessarily meaningful, but it's...
Yeah, I mean, I'm not sure. Yeah, I'm not sure if that's the right question to study about these things. Well, so here's one result that Federico and Carly Klivans proved, which is that the Bergman complex of a matroid is homotopy equivalent to a wedge of spheres. So that's
To a wedge of
spheres.
spheres.
Yeah. So I mean, it's very nice topologically. So now I can introduce the positive-oriented analog of the Bergman complex. And then I'll get to some results about these things, so you can see that they're actually quite nice to study. How am I for time, by the way?
Oh, probably until about 1 hour or so, because we started quite late, so.
Okay.
Like,
Okay.
Yeah, 15, 18 minutes, something like that. Should that be okay, you think?
Oh, okay. Yeah. I mean, I could probably talk longer, but yeah, that should be fine. Okay. So here is the definition of the positive.
Oh, we also are interrupting you a lot, not to interrupt, to tell you that. And so Kristen is reminding me that, if you need some more time, take
I
some
think
more
she
time,
can
'cause
have maybe not
we've
quite
interrupted
a
you a lot, and we will
Okay.
continue to.
Not quite to.
Okay. I mean, it's kind of a matter of whether or not I give you the fuzzy versions of the next couple theorems or the technical versions.
We like fuzzy.
Okay. All right.
At this hour of the morning,
Okay,
my brain
okay.
can't do much more than a fuzzy now.
Okay. All right.
He wants. Okay, I don't know. You can split yourself in two
I want
and
the
give
real
2
theorem.
lectures.
I also have less theorems, but the real
Sorry,
theorem.
Lauren.
I could write out fuzzy versions and then kind of
It's fine.
say.
Just he complains more than I do. Do the precise versions.
I mean, either way is fine.
Whatever you feel like at the moment in which you're writing it.
Okay. I mean, there's something cool at the end that I do want to have time for, so I might give fuzzy versions of the next couple theorems. So here is the positive Bergman complex of an oriented matroid. So this time we start with an oriented matroid. And we again call its circuits C. And now, so here's the definition. The positive Bergman complex, denoted B plus of M, is, this time it's the set of weight vectors such that every circuit achieves its maximum weight in the positive part of the circuit and also in the negative part of the circuit. So you can see how this is a more special version than the previous definition. Well, if I hadn't erased the example that I had just drawn, instead of getting the 3 different rays, you would have gotten 2 rays. So it's the subcomplex of it. Okay, so now...
Just help me to understand that example. Why would I have gotten only 2 rays?
So that's because the circuits were 1, 2, 3 bar, and we want the maximum to be achieved in the positive part and in the negative part. So this means that either omega 1 is omega 3 greater than or equal to omega 2, or omega 2 is equal to omega 3.
Ruled out one of the 3.
That's right. Yeah. Okay, so at this point, let me give fuzzy versions of a couple of theorems. Okay, so the first theorem is a theorem of Federico and Klivans. And so this is the non-technical version, but it says that essentially the Bergman complex of M has a nice description in terms of the matroid M, which implies that B of M is homotopy equivalent to a wedge of spheres. So the technical version of this theorem is that a certain subdivision of the Bergman complex is a geometric realization of the order complex of the lattice of flats of this matroid. And because lots of things are known about order complexes of lattice of flats, this implies that it's homotopy equivalent to a wedge of spheres.
You take the order complex of the lattice of spheres.
Lattice of flats of the matroid.
Of flats.
Mm-hmm.
And which you have to, this one you have to subdivide, or that one you...
Yeah, this one you have to subdivide. And you subdivide it based on certain equivalence classes on these weight vectors. So you see, the thing is that the Bergman complex, so you subdivide it according to the relative order of these omega i's. And this subdivision is a geometric realization of the order complex of the lattice of flats. And so then the analogous theorem, which was with Ardila, Klivans, and myself, is that B plus of M has a nice description in terms of M, where now M is an oriented matroid. And this nice description implies that B plus of M is homotopy equivalent to 1 sphere. And the technical version of this theorem is the analogous statement, except you replace the lattice of flats with the Las Vergnas face lattice of the oriented matroid.
So this, what's the dimension of this sphere? It's just the rank of the matroid, or?
Yeah, I believe it's the rank of the matroid. That's Federico's nodding. Yeah.
So this is sort of the same sphere that you would get when you take the representation by
Pseudo-line arrangement?
Pseudo-lines or
I'm not sure actually. I don't know that much about the arrangement, but
it's just one thing.
okay. And one thing is that if you start with so if M is an oriented matroid, a priori its underlying matroid has multiple different possible orientations. So as you vary the orientation, you will get a covering of the Bergman complex of M. Okay, so now let me talk about, well, actually I could show you now the picture of the Bergman complex of this matroid. It's quite pretty. So the Bergman complex corresponding to this matroid is the following. And now I should tell you what the labels on these points are. And remember that the description of the Bergman complex is in terms of the lattice of flats of the matroid. So in particular, all of the labels that I show here are flats of this matroid. But there's actually some extra, well, so you might recognize this as the Peterson graph, except there are some extra subdivision points. And the connection with the weight vectors is as follows. So this point 1 is representing the set of weight vectors such that omega 1 is less than omega 2 equal omega 3 equal ... Omega 6, this 1, 2, 5 represents the collection of weight vectors such that omega 1 equal omega 2 equal omega 5 less than the rest of them. And this edge here represents the weight vectors such that omega 1 is less than omega 2 equal omega 5 less than the rest. So this is an example of the connection between the lattice of flats in the matroid and the Bergman complex. Okay, so now let me go to, and actually let me point out that the positive Bergman complex is going to be well, it depends on, so for this particular oriented matroid, the positive Bergman complex will be this particular sphere. Okay, so now let me go to the case of a Coxeter arrangement.
I just want to start a question first. Is it clear that the Peterson graph is homotopy equivalent to a wedge of spheres?
I was thinking the same stupid question, so I'm really happy.
One-dimensional complex.
Good point. Yes.
Thank you.
Good, okay. Still, thank you for asking. I was trying to think in a complicated way. Yeah, you're right.
So now this is going to be the Bergman complex of a matroid for M, the matroid of a Coxeter arrangement. Do people here know about root systems and Coxeter arrangements? Okay, well you don't actually have to know anything about these things, but Coxeter arrangements are certain classes of hyperplane arrangements, and they're in bijection with configurations of vectors which are known as root systems.
The hyperplanes of reflection for a finite reflection group?
Yes.
Okay.
Yes. Yeah, crystallographic root systems is another way.
They have to be crystallographic, or could you have a hyperplane arrangement corresponding to H4 or something?
Oh, actually, I think that's also called a Coxeter arrangement. Yeah, actually, we haven't quite finished figuring out in what generality these results are true, so for now I'm going to assume a crystallographic arrangement. Okay, but you don't actually have to know anything about Coxeter systems. But just to set things up correctly, let's let capital Phi be a crystallographic root system, and let's let M sub phi be the corresponding matroid. And now, of course, our goal is to describe B of M sub phi and B of M sub phi plus explicitly. So if you don't know what Coxeter arrangements are, let me just say that the Coxeter arrangements that I care about correspond to what are called crystallographic root systems, which in turn correspond to certain graphs called Dynkin diagrams. If you don't know what any of these words are, it doesn't really matter, because everything I do will just be in terms of a particular graph. But one example of a Dynkin diagram is the following simple graph. All of the graphs that I'm going to be dealing with are actually very simple kinds of trees. Okay, but now let me actually introduce another object, which is a very cool kind of a polytope called a graph associahedron. This is a polytope that was invented just in the last year or so and generalizes the ordinary associahedron and also the cyclohedron. Cyclohedron? So I'm going to describe a procedure for starting with a graph and then building a particular kind of polytope associated with that graph. Okay, so, well, as I said, these are polytopes generalizing the associahedron and the cyclohedron. Okay, so here is the procedure for building one. So let's start with a graph, G, say on n vertices. And now what we do is we take a simplex of dimension n minus 1. So its facets are in bijection with the vertices. Take a simplex of dimension n minus 1 and choose some bijection between its facets and the vertices. Let me do a running example. So let's say that we start with the graph. Well, it's a Dinkin diagram of type D4. Okay, and now let's draw some simplex of dimension 3. And let's choose a bijection between the vertices and the facets of this thing. So this outer facet here will correspond to this point. And this bottom facet will correspond to this point. This outer facet is the middle point, and then this back facet is the leftmost point. Okay, so now what we do is, so first of all, if we have a bijection between facets and the vertices, this implies that any connected subgraph of G determines a face of the simplex. You just look at the intersection of the corresponding facets. Okay, and now what we do is we're going to start truncating this simplex according to connected subgraphs. So for each n-1 vertex connected subgraph of G, let's truncate the corresponding face of the simplex. So I'll see if I can draw this properly. Okay, so one connected three-vertex subgraph is these three vertices, and they correspond to, well, this, and this vertex, which determines the top vertex. So now we want to truncate the polytope here, and we get this. And now the other things that we're going to truncate are going to be this vertex and also this vertex. So we're going to get something that looks like this, and something that looks like this. Okay, and then we do the same thing for each n-2 vertex connected subgraph, and for each n-3 vertex subgraph, etc. So we also do some more truncations, and it's a little complicated to draw. So I won't draw the resulting polytope, but anyway, this is one definition.
Truncate for the whole graph, because that would just erase the point.
Yeah, and also you don't truncate facets because that doesn't change it combinatorially.
Change it.
Yeah. And so anyway, if you start with just a path and perform this procedure, you're going to get the usual associahedron. And there's a very easy bijection that will allow you to see that. And if you start with this circular chain then you're going to get the cyclohedron. Okay, so okay, so now let me just write down our theorem. This is with Federico, Reiner, and myself. And what we showed is that the positive Bergman complex of this matroid of a Coxeter arrangement is dual to the graph associahedra of type phi. And by type phi, I just mean the graph associahedra corresponding to the Dinkin diagram of phi. So
in the usual sense of points going to facets and
sorry?
dual in the usual sense of geometry, points going, vertices going to facets and all the...
Yeah, that's right. Yeah, that's right. Yeah. And we also have another description of the Bergman complex of the usual matroid, but that would require more definition, so I think I'll stop here.
What do these graph associahedra look like? I mean, for example, if you do this for types dn or in whatever or something, do you get polytopes that occur in other contexts, or do you just get sort of new polytopes?
I'm not sure if that's known, actually. I mean, I can show you a picture of the D4 associahedron,
It's
but
the thing when you truncate it on 3 more edges, right?
Right. I mean, I'm not sure if that has appeared in particular in another context. I mean, these things were just introduced a year ago. So things like their F vectors are known. You know, we can completely describe the posets, but.
Who introduced them?
Oh, I should have said that. They were introduced by, well, they were discovered independently by Carr and Devitis, and they came up with this definition by truncating a simplex, and also simultaneously Alex Postnikov introduced them, but he built them as a Minkowski sum of simplices.
Actually, I think earlier they were introduced by Mike Davis.
Right, although in a very different context.
And I think and I guess what he was trying to do, if this means anything, is to, compactify the complement of the Coxeter complex. And these things are right naturally in that context.
The Coxeter complex is...
I'm sorry?
When was that?
Maybe 3 or 4 years ago?
He actually, I mean, I know that Devidos worked quite closely with him. So probably some of his work came out of their work.
There's Burkman complexes. What's the main motivation for their introduction? Is it this that they provide a geometric realization of the?
I mean, they were introduced simply as an.
Or?
No, that wasn't the motivation, since it wasn't known at the time. The motivation was to build an analogy to tropical varieties. So here's a picture. This picture represents the set of all varieties. This represents the subset of linear varieties, varieties defined by ideals generated by linear forms, and then matroids generalize linear varieties in another direction. So tropical varieties are things defined over here, and then Bergman complexes are defined over here. I think that was the main motivation. And so, of course, because matroids generalize linear varieties, proving things about the Bergman complex proves things about tropical varieties associated to linear ideals.
I guess also to some extent these tropical varieties are appearing in lots of different places, and if you've heard about amoebas There are these objects that are kind of appearing in a lot of different areas, and the question was just if we can say anything about the topology of these tropical varieties, because it's very difficult to say anything about them, and even this linear case, the case of the matrix, is really the only case where
people can say
people know what they look like.
Scott gave some talks on amoebas here a year ago.
Where's Scott now?
Where is Scott now? Berkeley or Princeton or NYU? I'm not sure. But he's going to Princeton.
Yes.
Yeah. He got a deal from NYU, but he doesn't have to show up there for 2 years. He doesn't have to